Pluto is a distant and mysterious dwarf planet, which was once a member of our solar system's planetary family. However, recent startling announcements by leading astrophysicists Neil deGrasse Tyson and MIT's Michio Kaku have brought Pluto back into the spotlight with a shocking revelation. They suggest that this icy world is on a potential collision course with Neptune. But how could this happen, and what would be the consequences of such a massive event? Are we witnessing a rare astronomical phenomenon? Or is there something more to this impending cosmic collision? Join us as we explore the possibilities of a Pluto-Neptune impact. Pluto, a former planet that was demoted to a dwarf planet partly due to its peculiar orbit, remains a subject of fascination and study in the astronomical community. According to recent predictions by leading scientists, Pluto's trajectory is dangerously close to Neptune's. Astrophysicists Neil deGrasse Tyson and Michio Kaku are both raising the red flag of a possible hazardous collision between these two planets that could be a huge threat to Earth. How is such an event even possible? Pluto's journey around the Sun is unlike any other planet in our solar system. It takes a staggering 248 years to complete a single orbit, meaning since its discovery in 1930, it hasn't even finished one full revolution. But the intrigue doesn't stop there. Pluto's path is marked by its highly elliptical shape, deviating significantly from the near-circular orbits of the major planets. What makes Pluto's orbit even more peculiar is its inclination, angled at 17 degrees to the ecliptic plane. The path Pluto traces is much steeper compared to the other planets. This inclination and elliptical nature add layers of complexity to its orbital pattern. One of the most intriguing aspects of Pluto's orbit is its intersection with Neptune's path. For about 20 years in each orbit, Pluto actually comes closer to the Sun than Neptune, defying what we might expect from their positions in the solar system. This leads to the natural question: why hasn't Pluto collided with Neptune? The answer lies in the gravitational influences of other planets. The study of Pluto's orbit began soon after its discovery. Initially, astronomers struggled to understand its unique trajectory. Unlike the other planets whose orbits lie relatively close to the ecliptic plane, Pluto's path stood out with its steep inclination and elliptical shape. The mystery deepened with the realization that Pluto's orbit actually crosses Neptune's. The stability of Pluto's orbit amidst these complexities is proof of the intricacies of space mechanics. The three-body problem in space is about figuring out how three things in space like Pluto, Neptune, and the Sun move and affect each other with their gravity. It's like trying to predict where they will go based on where they start and how they pull on each other. In Pluto's case, this problem shows how its path, Neptune's path, and the Sun's gravity all work together in a complex way. The terms asymmetrical libration and latitude libration, along with the VZK oscillation, are part of this puzzle. According to astrophysicists, what's keeping all planets in their orbits is an asymmetrical libration. In the context of Pluto and Neptune, this term means that whenever Pluto crosses Neptune's orbit, it's positioned at least 90 degrees away from Neptune. This spatial separation is crucial in preventing their paths from colliding. Latitude libration, on the other hand, refers to the vertical movement of a celestial body in its orbit. For Pluto, this means that when it comes closest to Neptune or any other giant planet, it's situated significantly above their orbital plane, providing an additional layer of protection from potential collisions. Another crucial component in this equation is the VZK oscillation. This is named after three scientists, von Zippel, LV, and Kai, who studied how things move in space. It's about how three space objects like Pluto, Neptune, and the Sun pull on each other with their gravity. This pulling affects how they move. In Pluto's case, VZK helps us understand why its path around the Sun is so unusual. Even though Pluto's path seems all over the place, this oscillation helps keep it moving smoothly for a long time. The VZK oscillation shows that even if things in space seem wild and random, some patterns and rules keep everything in order. All of these components help keep Pluto's orbit stable, making sure it doesn't crash into Neptune or get thrown off course. This three-body problem helps in understanding how these paths change because of the way these space objects pull on each other. Studying this helps us learn about Pluto, our solar system, and distant worlds and their stars. Numerical simulations in the late 1980s revealed that despite these stable properties, Pluto's orbit is technically chaotic, with minor deviations in initial conditions leading to significant differences over millions of years. However, these unique properties of Pluto's orbit have been found to maintain stability over incredibly long timescales, effectively keeping the chaos at bay. Recent computer tests have helped us understand how the big planets like Neptune, Jupiter, and Saturn affect Pluto's path around the Sun. Neptune has a special connection with Pluto where for every 2 rounds Pluto makes around the Sun, Neptune makes 3. This connection helps keep Pluto's path steady. But Neptune isn't the only one helping. Jupiter's gravity also plays a big part in keeping Pluto's orbit safe and stable, and Saturn helps a bit too. These tests show that Jupiter's gravity alone is strong enough to make sure Pluto stays on a stable path for a really long time, even billions of years. So, it's like Neptune, Jupiter, and Saturn are all working together to make sure Pluto keeps moving safely in space without running into trouble. These phenomena are essential in the context of the universe for maintaining the order and predictability of space bodies' movements. Without these mechanisms, the solar system as we know it would be a place of much greater chaos and unpredictability. Bodies like Pluto could potentially collide with others or be ejected from their stable paths, leading to a domino effect on other celestial bodies. For Pluto, especially with talks about it possibly crashing into Neptune in the future, understanding its orbit is really important. This gives us a clearer picture of the solar system's dynamic nature. The case of Pluto demonstrates how even the most seemingly unstable orbits can achieve a state of equilibrium through the complex interplay of gravitational forces and orbital mechanics. It also shows the importance of continuous observation and study of these phenomena to grasp our place in the universe better. Exploring the depths of space often leads us to confront the unpredictable nature of celestial bodies, and Pluto's orbit is a prime example of this unpredictability. The concept of orbital chaos, which refers to the sensitive dependence of a celestial body's path on its initial conditions, is vividly illustrated in the case of Pluto. This means that even slight variations in the dwarf planet's position or velocity can significantly change its long-term orbit. Pluto's status as a celestial enigma continues to captivate astronomers and space enthusiasts alike. Discovered in 1930 by Clyde Tombaugh, Pluto was initially hailed as the 9th planet in our solar system. However, its classification underwent a significant revision in 2006 when the International Astronomical Union redefined the criteria for what constitutes a planet. Pluto, due to its size and characteristics, was reclassified as a dwarf planet, sparking debates and discussions about its nature and place in our cosmic neighborhood. Despite its reclassification, Pluto remains a crucial object of study in the field of astronomy. Its unique orbit and relationship with Neptune have particularly intrigued scientists, prompting extensive research and theoretical studies to understand its dynamics and potential interactions with other celestial bodies. The discovery of Pluto was a significant milestone in the history of astronomy. Clyde Tombaugh's meticulous observations from the Lowell Observatory in Flagstaff, Arizona, led to the identification of a faint moving object beyond the orbit of Neptune. This discovery not only expanded our understanding of the outer solar system but also raised questions about the nature of Pluto itself. Initially, Pluto's size was overestimated, leading to its initial classification as the 9th planet. However, subsequent observations and advancements in astronomical techniques revealed Pluto's diminutive size, comparable to that of some moons in our solar system. This realization prompted discussions among astronomers about how to classify Pluto accurately within the hierarchy of celestial bodies. One of the defining features of Pluto is its highly eccentric orbit. Unlike the relatively circular orbits of the major planets in our solar system, Pluto's path around the Sun is significantly elongated and tilted. This elliptical orbit takes Pluto from approximately 29.7 to 49.3 astronomical units (AU) from the Sun. An astronomical unit is the average distance between the Earth and the Sun, approximately 93 million miles, 150 million kilometers. The eccentricity of Pluto's orbit contributes to its complex relationship with Neptune. Despite being much smaller than Neptune and residing farther from the Sun, Pluto's orbit occasionally brings it closer to the Sun than Neptune. This peculiar orbital configuration raises questions about the potential for gravitational interactions and collisions between these two distant worlds. The orbital periods of Pluto and Neptune also highlight their unique dance around the Sun. While Pluto takes about 248 Earth years to complete one orbit, Neptune orbits the Sun once every 165 years. This difference in orbital periods means that Pluto and Neptune periodically cross paths, albeit without colliding due to the gravitational influences of other planets and orbital mechanics. The gravitational relationship between Pluto and Neptune is governed by complex dynamics involving their masses, distances from the Sun, and orbital velocities. Despite their occasional close encounters in orbit, these celestial bodies follow predictable paths due to the principles of celestial mechanics elucidated by Isaac Newton and refined through subsequent scientific advancements. The stability of Pluto's orbit amidst its eccentricity and interactions with Neptune can be attributed to several factors. One crucial aspect is the gravitational influence of larger planets such as Jupiter and Saturn. These gas giants exert significant gravitational forces that help stabilize the orbits of smaller bodies like Pluto within the solar system. Numerical simulations and theoretical models have demonstrated how Jupiter's gravitational pull acts as a gravitational anchor, maintaining the relative stability of Pluto's orbit over long timescales. Without Jupiter's influence, Pluto's orbit could potentially become more erratic, leading to increased chances of collisions or ejection from the solar system. Saturn's gravitational influence also plays a role in stabilizing Pluto's orbit, albeit to a lesser extent compared to Jupiter. The combined gravitational forces of these gas giants create a dynamic balance that helps regulate the orbital motions of Pluto and other objects in the Kuiper Belt, a region of the outer solar system populated by icy bodies and dwarf planets. In addition to external gravitational influences, Pluto's orbit is also shaped by its intrinsic orbital characteristics. The inclination of Pluto's orbit relative to the ecliptic plane, the plane in which Earth and the other major planets orbit the Sun, is approximately 17 degrees. This inclination contributes to the unique orbital dynamics observed in Pluto's path around the Sun. The intersection of Pluto's orbit with that of Neptune occurs during specific intervals in their respective orbital periods. This phenomenon results in close approaches between Pluto and Neptune despite their differing distances from the Sun. However, the gravitational interactions between these two bodies have thus far prevented any catastrophic collisions or significant perturbations in their orbits. Astrophysicists and planetary scientists continue to study the orbital dynamics of Pluto and Neptune using advanced computational models and observational data. These studies aim to refine our understanding of the long-term stability of their orbits and to predict future interactions between these distant celestial bodies. The concept of orbital resonance is particularly relevant in understanding the relationship between Pluto and Neptune. Orbital resonance occurs when two celestial bodies exert periodic gravitational influences on each other, causing them to oscillate or synchronize their orbits over time. In the case of Pluto and Neptune, a unique resonance pattern known as a 3:2 mean motion resonance exists. This resonance means that for every 3 orbits Pluto completes around the Sun, Neptune completes approximately 2 orbits. This resonance pattern helps maintain the relative stability of their orbits and minimizes the likelihood of close encounters or collisions between the two bodies. The phenomenon of mean motion resonance is not unique to Pluto and Neptune but is observed in other celestial systems as well. It exemplifies the intricate gravitational interactions that govern the dynamics of planetary orbits and underscores the delicate balance that exists within our solar system. The stability of Pluto's orbit is also influenced by orbital librations, which refer to periodic variations or oscillations in the orientation of its orbit relative to other celestial bodies. These librations help regulate Pluto's orbital inclination and maintain its overall orbital stability over extended periods. Astrophysicists and planetary scientists utilize advanced numerical simulations and computational models to study the orbital dynamics of Pluto and other celestial bodies. These simulations involve calculating the gravitational interactions between multiple objects in space and predicting their orbital paths over millions or even billions of years. By simulating various scenarios and inputting different initial conditions, scientists can explore the potential outcomes of gravitational interactions between Pluto, Neptune, and other celestial bodies. These simulations provide valuable insights into the long-term evolution of the solar system and help elucidate the mechanisms that govern planetary orbits. The study of Pluto's orbit also offers insights into the broad field of celestial mechanics and orbital dynamics. The principles and mathematical equations developed to describe Pluto's orbital motion can be applied to understand the orbits of other planets, moons, asteroids, and comets within our solar system and beyond. The discovery of Pluto's moons, Charon, Nix, Hydra, Kerberos, and Styx, has further enriched our understanding of its orbital dynamics and gravitational interactions. These moons exert gravitational influences on Pluto and contribute to its overall stability within the Kuiper Belt region. Charon, in particular, has a significant gravitational influence on Pluto due to their close proximity and relatively large size ratio compared to other moon-planet systems in the solar system. The gravitational interactions between Pluto and Charon have resulted in tidal locking, where the same side of each body constantly faces the other as they orbit around their common center of mass. The study of tidal lock and gravitational resonances between Pluto and its moons provides valuable insights into the processes of planetary formation and evolution within our solar system. These processes are influenced by gravitational interactions, collisions, and orbital dynamics that shape the structure and composition of celestial bodies over billions of years. Pluto's classification as a dwarf planet has sparked debates about the definition and categorization of celestial bodies within our solar system and beyond. The International Astronomical Union's decision to reclassify Pluto in 2006 prompted discussions among scientists, educators, and the general public about the criteria used to define planets and their subclasses. The criteria for defining planets as established by the International Astronomical Union include three primary conditions. The celestial body must orbit the Sun, it must be spherical in shape due to its own gravity, and it must have cleared its orbital path of other debris or smaller objects. Pluto meets the first two criteria as it orbits the Sun and is roughly spherical in shape, albeit with a slightly elongated and irregular shape compared to the major planets. However, Pluto does not satisfy the third criterion of clearing its orbital path of other objects, particularly within the densely populated Kuiper Belt. The Kuiper Belt is a region of the outer solar system beyond the orbit of Neptune that contains numerous icy bodies, dwarf planets, and small celestial objects. Pluto shares this region with other Kuiper Belt objects, including Eris, Haumea, and Makemake, which are also classified as dwarf planets due to their size and characteristics. The discovery and exploration of the Kuiper Belt have provided new insights into the diversity and distribution of celestial bodies within our solar system. These icy remnants from the early formation of the solar system offer clues about its origins and evolution over billions of years. The New Horizons mission launched by NASA in 2006 provided unprecedented observations and data about Pluto and its moons during its historic flyby in July 2015. The spacecraft's images and measurements revealed detailed information about Pluto's surface features, atmospheric composition, and geological characteristics. In conclusion, Pluto remains a fascinating celestial object that continues to intrigue scientists and enthusiasts alike. Its unique orbit, gravitational interactions with Neptune, and classification as a dwarf planet highlight the complexities of our solar system's dynamics. Through advanced research and exploration, we continue to unravel the mysteries of Pluto and gain deeper insights into the formation and evolution of our cosmic neighborhood.